Hi, I'm going to go through a couple of problems. The first one that I'm going to do is a free response question that people were a little bit tripped up on the note cards. So that more specifically was this one: when you're given a water tank with G gallons initially being filled at the rate F of T gallons per minute and emptied at the rate E of T gallons per minute. So it's being filled and it's being emptied. What is the amount of water in the tank at M minutes? And so we know to get from a rate to an amount, we have to take an antiderivative, right? And it's filling and emptying, so you do filling minus emptying. But what is this G business that was getting a lot of people? Well, that's an initial amount. So we have to start from where we were and then, from 0 minutes to M minutes, add up the amount that's being added to that. Then to find the rate the water amount is changing, you would just take the derivative of this. And so the derivative of G is 0, and the derivative of the antiderivative brings you back to the function itself. So we would just get the function itself evaluated at that M, right? F of M minus E of M. So that's how you get this one here. And then the time at which the water is at a minimum, well, to minimize, you just find the derivative, which we just found, and then you set it equal to 0, or you look where it's undefined. In this case, you don't have to worry about the undefined. So you just do F of T minus E of T equals 0. And then, of course, if you want the absolute minimum, you have to evaluate the endpoints too. So to evaluate the endpoints, you would put it back into the original function, and you would find the minimum value. So that's a lot, right? Let's apply that. And let's apply that by doing this problem here. We have oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. So you see the units there? That indicates that is a rate. So the units are going to be a huge, huge thing for us. So remember to look at units to help us determine what we're looking at. The oil slick takes the form of a right circular cylinder. So it is a cylinder that we're dealing with both the radius and the height changing over time. So that might be an important piece of information if we have to take a derivative. So keep that in mind. So part A says, at the instant when the radius of the oil slick is 100 centimeters, so when the radius is 100, see how it says centimeters there? That is an indication that that is going to be an amount and not a rate. And the height is 0.5 centimeters. So the height is 0.5, and we're dealing centimeters and centimeters. So that is good news for us. The radius is increasing, so dr dt equals 2.5, and that's positive because it's increasing. At this instant, what is the rate of change of the height? So we want to find dh dt. Also, if we look back at what I underlined, it says that the volume increases at a constant rate. So that's the volume, dv dt, equals 2,000. And if you look at the units, cubic centimeters per minute, you know that is a cubic thing. So that must be a volume type thing, right? Okay, so we know that volume is pi r squared h. Now let's underline the variables that are changing over time, the volume, and remember it told us that both the radius and the height are changing over time. So that is an indicator that if we are to take the derivative, dv dt, we must use a product rule because we have pi r squared times h. So pi, the derivative of r squared, is 2r dr dt, because that radius is changing over time. It's got a baby. Derivative of the first times the second plus the first, which is our pi r squared, times the derivative of h is 1 times dh dt. Excellent. So now we have a lot of information. We have 2,000 equals pi times 2 times our r, which is 100, times our dr dt, which is 2.5, times our height, which is 0.5, plus pi radius squared times dh dt, which is what we are trying to find. And then we would simply put all that in our calculator and solve for dh dt. And our units would be centimeters per minute, right? So I'm not going to do that on my calculator right now. That's how you do that problem there. So now I'm going to tackle part B. They tell us a recovery device arrives on the scene and begins removing oil. So remember when we were looking at the note card, we were doing fill minus the emptying. So now we are removing. We are going to be emptying something. And this is RT, and it is in cubic centimeters per minute, which means it is a rate, which it tells us that it's the rate anyway. But remember, units are helpful. And the oil continues to leak at a rate. This is also a rate. So this is what is filling and this is what's removing, right? Because it's leaking, so it's adding to our oil slick, and then we're removing it here. Find the time when the oil slick reaches its maximum volume. So we know it's going to reach its maximum volume when dV dt equals 0. So what is dV dt? That would be the rate at which it's filling up. So that's the 2000. Minus the rate at which this thing is emptying. So that would be 400 root T. So again, this is the fill rate, this is the empty rate. And to maximize, we want to see where it is changing from. Maximize would be positive to negative. So we want to see where it's changing from positive to negative. So dV dt equals 0 when 2000 equals 400 root T. Divide both sides by 400. 5 equals root T. So T equals 25. So I guess I shouldn't have put the plus and minus on here until I verified, but let's just go ahead and do that now. So if I put in like a 0, for instance, I would get 2000 minus 0, which is indeed positive. If I put in a number bigger than 25, then of course this would be negative. And so this does check out since dV dt changes from positive to negative at t equals 25 minutes. And I should have put my units there. This is minutes, right? And if I want to say that it's the absolute maximum, remember, let me just write this for a second. Since dV dt changes from positive to negative at t equals 25 minutes, and dV dt is greater than 0 for all t less than 25, and dV dt is greater than 0 for all t greater than 25, we know t equals 25 minutes maximizes our volume. Since it only switched sign that once, we know that whatever our local was must be our absolute. In this one, we don't really have any endpoints to check, right? If the radius was 0 or the height was 0, then the volume would be 0. And so this is just one of the cases where, it was always increasing and then always decreasing. And so obviously that local must be an absolute, right? So now I'm going to go ahead and do part C. By the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Write but do not evaluate an expression involving an integral that gives the volume. So we had a rate here, so we want to go from a rate to an amount. So the way I like to think about these is we know some information. We know specifically that V of 0 is 60,000, and we want to find V of t. So that would help us set our bounds of our integral, because we know that the antiderivative of the derivative is going to bring us back to the volume itself, right? From 0 to t. So we have V of t minus V of 0 is going to be equal to this antiderivative. In other words, if I add V of 0 to both sides, I have that V of t is equal to V of 0 plus the integral from 0 to t of that dV dt. And I really should be using a different letter here. So let me just change this all to an x so we don't get confused. So what is V of 0? That V of 0 is the 60,000 plus the integral from 0 to, in this case, it says the time found in part B, so that's 0 to 25, because we just found that, of our dV dt, which was 2,000 minus 400 root t dt. And that's all I have to do for that part of the problem. Now, if we look back at the note card, we can see how that makes sense because it was just saying that we had the original amount plus the integral from 0 to whatever our time is of the fill minus the emptying. And that is exactly what we just proved here. So I honestly just usually look at the pieces of information that I'm given. So in this case, I was given at 0 and I wanted to find at some time t, which I ultimately ended up calling an x here. So what I did was I used that as my bounds of integration so that I could discover what that v of x was, and I wouldn't forget to add in my initial because I started somewhere. I didn't start at 0. It's kind of like throwing a ball. You know, if you're at a height of 10 feet and then you throw the ball up, you have to account for where you started when you're finding the ultimate height of the thing. So that's that same idea, is that you have to remember that initial condition. And I just like to think of it as whatever I'm given and whatever I'm trying to find, that's how I find the bounds of integration. So let me show you one other problem that's like that to make this clear. I'm going to go ahead and do number 5, just part D. They tell you that f of 1 is 3 and that you need to find f of 4 and f of negative 2. What's given in the graph is f prime. So we know that the antiderivative of f prime is going to bring us back to f. So they ask us to write an expression for f of x. Before I do that though, I'm going to just do something more concrete. So I'm going to actually find f of 4, I'm going to find f of negative 2, and then I'm going to use that information to come up with the general equation. So that's just how I'm going to approach this problem. Also, if we read through the problem, they tell us that the area between negative 2 and 1 under the curve is 9. So this area is 9. And then this area between 1 and 4 is 12. So we know that this area underneath of there is 12. We're going to probably use that information when we're solving. So the first thing I'm going to do is I'm going to figure out what f of 4 is. So the way I like to approach this is I'm given information about f of 1 and I'm trying to find f of 4, and I know that the integral of f prime is going to bring me back to f. So again, I have information about 1 and 4, so that's how I determine the bounds of my integral. The integral from 1 to 4 of f prime of x dx is the antiderivative of f prime, just brings me back to f. I'm evaluating that between 1 and 4. So I have f of 4 minus f of 1. I want to solve for f of 4, so I'm going to add f of 1 to both sides. So that leaves me with the integral from 1 to 4 of f prime of x dx plus f of 1 is equal to f of 4. In other words, f of 4 is f of 1, which was my starting point, plus whatever the area under that f prime curve is from 1 to 4, right? Because I have my starting point plus whatever area I'm accumulating under the curve, and that's going to bring me to where I am for f of 4. Now I have some numbers to plug in. I know f of 1 is 3 because that's given information, and then the area under my curve from 1 to 4, under my f prime curve, is negative 12 because I'm going down. So minus 12 is equal to negative 9. Now the next thing they ask us to do is f of negative 2. So I'm going to apply that same type of logic, except now I'm going to use the integral, and since I go small number to big number, I'm going to go from negative 2 to 1, because again, I'm trying to find negative 2 and I'm given information about 1, so that determines my bounds. So from negative 2 to 1 of f prime of x dx is going to be the antiderivative of f prime is just f evaluated between negative 2 and 1. So I have f of 1 minus f of negative 2. In this one, I want to solve for f of negative 2. So I'm going to scoot that over on this side, and then I'm going to scoot the integral over on this side. I'm going to do 2 steps in one. So again, scoot the f of negative 2 over here, and then put this on this side. So I have f of 1 minus the integral from negative 2 to 1 of f prime of x dx. So that gives us 3 minus, and then the area under the curve between negative 2 and 1 is negative 9, because again, that's under the x-axis, so I need to subtract it out. So minus a negative 9, because again, this is minus, and then this integral is negative 9. So I have 3 plus 9, which is 12. The final thing that they're asking us to do is to write a general expression. What did I do? I'm just going to look at my answer here to figure out what that is. In general, my f of x is going to be given by my starting point, which is 3, plus the area under the curve from 1 to whatever x I'm going to, of f prime of x dx. And that's in general how I'm going to do it. The only reason it was flipped here to a negative is because you see that I went from smaller number to bigger number. So isn't that equivalent to the opposite, which is positive 1 to negative 2 f prime of x dx? Yes, indeed it is. And so that does hold to my formula. So that would be the answer to the general equation. The next thing that I want to go over is something we haven't done a lot of. Given the equation of f of x and h equals f inverse, find h prime. So you need to memorize this formula. Let's memorize it right now. Let me just show you how this works. The derivative of f inverse is 1 over f prime of f inverse. You need to memorize that. So please write it down, memorize it now. If they tell you f of x equals x cubed minus 1, find the value of the derivative of f inverse of 7. So d dx of f inverse of 7 is going to be 1 over f prime of f inverse of 7. We always start in the inside because I want to do f prime of f inverse of 7. In order to do that, I must first find f inverse of 7. So f inverse of 7 means when y equals 7, what is x? Because remember, in inverse function, we swap the x and y. So remember that f of 7 just means when x is 7, what is y? So this one, you just swap it. When y is 7, what is x? So let's figure that out. When y is 7, what is x? X cubed minus 1, 8 equals x cubed, x equals 2. Beautiful. So I have 1 over f prime of 2. So what is f prime of 2? Well, f prime of x is just 3x squared minus 0. So f prime of 2 is going to be 3 times 2 squared, which is 3 times 4, which is 12. So my answer is 1/12. Okay, so let's just do a couple more practice problems here. So let g and h be inverse functions, and we have a table of values. So they want us to find h prime of 1. So again, g and h are inverses. Let's just rewrite our formula. So the derivative of the inverse is equal to 1 over f prime of the inverse. So in this one, g and h are inverses. So we want to find the derivative of h, which is the inverse of g. So I'm going to just rewrite it with the same notation. I get 1 over g prime of g inverse of x. I want to find it at 1, so I'm going to be doing g inverse of 1. G inverse of 1 is the same thing as h of 1. H of 1 in this case is 3. So I get 1 over g prime of 3. And then g prime of 3 is negative 2. So I have negative 1/2. Yay! Same type of question here. They want us to find g prime of negative 2. And again, f and g are inverses. So d dx of, that's f inverse, right, of negative 2 is going to be 1 over f prime of f inverse of negative 2. And so f inverse of negative 2 is the same thing as g of negative 2, because again, f and g are inverses. So g of negative 2 is going to be 5, 1 over f prime of 5, and f prime of 5 is negative 1/2, and 1 over negative 1/2 is just negative 2. Yay! Now let's try one that is a little bit more difficult. So in this one, they want us to find g prime of 11, and they tell us that f and g are inverses. So g prime of 11 is going to be the derivative of f inverse of 11, because again, f and g are inverses. So that's going to be 1 over f prime of f inverse of 11. What does f inverse of 11 mean? That means g of 11, because f and g are inverses. Now, that's what we're looking for in the table, but we don't have a table in this case. So f inverse of 11 also means when y equals 11, what is x, right? We had just discussed that before, because inverses mean that you swap the x and the y. So we know when y is 11, x is 2. So this is simply 1 over f prime of 2. So what is f prime of 2? F prime of x is 3x squared plus 2. So f prime of 2 is going to be 3 times 2 squared, 4 plus 2. 12 plus 2 is 14. So I have 1 over 14. Yay! Let's just try one more of this type. So we want to find the derivative of f prime of 10, and now we have h and f are inverses. So the derivative of h inverse of 10, and so that's going to be 1 over h prime of h inverse of 10. And so h inverse of 10 again means when y equals 10, what is x? When y is 10, x is negative 1, 1 over h prime of negative 1. So h prime of negative 1, we need to find h prime of x. H prime of x is 0 minus 1 minus 10 x to the fourth. So h prime of negative 1 is going to be minus 1 minus 10 times negative 1 to the fourth. So that is going to be positive. So minus 1 minus 10 is negative 11. So I have 1 over negative 11 as my answer. Next up, let's just really quickly go over some of these common errors. So remember, if you want to do a point of inflection, you must show that f double prime changes sign. F changes concavity, f double prime changes sign. That is a point of inflection. You cannot just say it equals 0. You must actually show that it changes sign. Remember, that same type of thing holds true for a max or min. You must show that it changes sign, not simply that it equals 0, because otherwise it could just level out. That derivative equals 0 there, but it didn't change sign, so it wasn't a maximum or a minimum. So please make very, very certain of that. Don't ever do the average rate of change as this. The average rate of change, algebra 2 brain, that's just the slope, f of b minus f of a all over b minus a. If you want to do the volume of washers, I usually factor that pi out, but make sure you're doing radius outer squared minus radius inner squared and not doing radius minus radius and squaring the whole thing. That would be different. That would be a FOIL type thing. Remember, pi, integral, radius outer squared minus radius inner squared. When you have separable differential equations, so that's like when you have dy dx equals 2y over x or something like that, make sure that you separate the variables as the first step. Otherwise, you're going to lose a ton of points on the AP. So in this case, you would get 1 over 2y dy equals 1 over x dx. So make sure you do not forget that. When you are actually solving these separable equations, don't forget to add the plus c. You only have to add it to the right side. Whenever you're taking an indefinite integral, you need that plus c. Don't forget, because you're getting a family of functions as your answer. If you don't have the initial condition, you can't solve for that c, but if you do, then you know the actual particular solution. So just don't forget to add that plus c whenever you're dealing with an indefinite integral. Don't ever use the word it. I know I've said it in that video that you watched for 2 hours. I'm going to say it again. Don't say it. Say if f prime is changing from positive to negative, not if it is changing from positive to negative. Otherwise, you will not get credit. It will not give you credit. If the answers come from your calculator, put in what you did. So if you're using fnint on your calculator, you just write like 0 to 2 of f of x dx. Write that down, and then in your calculator you can do fnint. of y1 from 0 to 2, okay? Don't write that calculator talk on your paper. Don't write that you used FNIT, but just write what you did on your calculator, which was the integral. So people always do this one. If you have, for example, the antiderivative of 1 over y squared, people always want to do ln, absolute value of y squared. No, no, no. Okay, the only time you do ln is if you have 1 over y, particularly 1 over y. So the reason for the antiderivative of 1 over y is because that would be y to the negative 1. And so if you were to add 1, you would get 0 and then try to divide by 0. Nope, thou shalt not divide by 0. But if we have the integral of 1 over y squared, that is the integral of y to the negative 2, and you can just add 1 and divide by what you added, and that's how you do that one. So please don't apply the ln rule unless you actually need it. When you see d squared y over dx squared, that is the second derivative. That is simply a second derivative. So don't forget that notation because you don't want to mess it up just because you don't know the notation. And don't forget about the chain rule, okay? So if you're doing the derivative of this, then obviously it's a product rule. So you have 2x times y cubed, because the derivative of the first times the second, plus the first, which is x squared, times 3y squared times, they're forgetting their dy dx in this one because, again, we have implicit differentiation. Every y has a baby, so don't forget about that. If this was an actual question, they would probably ask you find d squared y over dx squared in terms of x and y only. And you see that we have the dy dx here. So what you should do is you should go ahead and replace that dy dx ultimately with what dy dx is in terms of just x and y, x squared, y cubed. And you plug it in right there, and then you could simplify. So that's it for this video. Hope it helped.